Hello and welcome to Team 14's presentation on Project 3, the Global Emergency Autonomous Response System, also known as the GEARS.
The main objective of the project was to develop a robot prototype also known as Global Emergency Autonomous Response System, otherwise known as GEARS. The GEARS robot had to be capable of autonomous navigation through disaster zones and transportation of much-needed supplies to affected communities in the zone. It also had to be capable of working in both natural and man-made zones and be versatile enough to work in a variety of cultures and regions. Specifically, the prototype had to navigate through a maze which simulated the disaster zone while avoiding hazards. Additionally, it had to transmit a map of the maze. An important aspect of the robot design involved it having a non-hostile appearance. Project management. The project's progress was monitored by documenting the team's meetings through in-detail meeting minutes, agendas, tasks completed, attendees, and action items in the design notebook. This turned out to be quite valuable in monitoring the team's progress and was also convenient for updating those members who could not make it to meetings. The team created a work breakdown structure for the design of the GEARS to manage the project. This helped the team identify and break down the main goals into smaller components or tasks associated with the project. This essentially helped organize the team's work into more manageable sections. A Gantt chart was created at the very beginning of the project with the help of the work breakdown structure to keep track of the responsibilities, tasks, deadlines, and progress. A functional block diagram helped the team identify the specific components of the gear. The main functions that the team had to focus on included path navigation, map production, hazard location and evasion, safe and secure cargo transportation, cargo deposition, and pickup signal. The team also constructed a needs-finding chart to recognize the customer needs and engineering requirements for the project. The team set target values for each technical specification. The success and the performance of the GEARS was later evaluated based on these target values.
On to evidence-based decision-making. First, we're going to be talking about the robot designs. Now, we had 4 designs originally, as shown on the right, top left being 1, top right being 2, so on and so forth. Now, what ended up winning was design 2, based on the streamlined nature of it and the non-threatening appearance and the container safety. Now, this was a little bit subjective though. So we went out and we decided to interview people from our class about how our robot looked how friendly it looked. Overall, we got about a 5 for the friendliness, but we didn't think that was enough. We wanted it to look more friendly. So in order to fix that problem, we added a top hat to the top of the robot's motor to kind of give it more of a whimsical feel and to make it seem less dangerous, because a motor sticking up out of the top of a robot could look threatening and could be perceived as a threat. Now we went ahead and we had to make decisions based on the cargo supply labels. And our original designs involved the food and water for sustenance / food and water. For shelter, we had people in a house. And for fuel, we had a tank of fuel, a fire, and a skull and crossbones, just to try to keep people away from it that didn't want it. And then for health supplies, we decided to have a heart and a bandage. And we ended up interviewing in the same survey. We found that everyone could figure out what each of those images meant. But that was not the issue. The issue came that people suggested that the medical supplies in the fuel were not an efficient and adequate way to describe how it should look. For example, the fuel looked rather threatening because of the skull and crossbones, and the medical supplies also looked threatening because of the heart. So instead, we removed the skull and crossbones from the fuel, and we ended up removing the heart and added a stethoscope and a bottle of pills. The other 2 remain the same. Okay, on to designing the robot, the design philosophy. Our first design, as shown, involved a wheel cage, which was used to keep all the wheels in place, and vertical motors to save on the space of the robot. Now, this ran into some issues though, namely that it was too large to effectively navigate through the maze. So in order to create a robot that was able to navigate through the maze, we had to remove the wheel cage, but we kept the vertical motors. And around the motors, we built a cage, as shown on the right here, over here, to hold up the ultrasonic sensors in the front, which also allowed for seeing dangers in front of it very efficiently. And additionally, that cage we made allowed us to make another cage to hold up the tall, small motor right there in the back. And additionally, when designing the robot, we had to think about cargo drop-off. So what we did was use a single vertical motor and a gear system to push the cargo off two sides. This was so in our original design, we had two smaller cargos on the sides, which we could then push off like that. But it was also easily changed to allow for using a single cargo by just removing one of the sides of the, as you can see right here versus over here. And additionally, the cage over the pie not only would keep the pie safe, it also was able to hold up this motor system and put it in a place where we thought it would be best for pushing off the cargo.
In order for the robot to meet project objectives, it was decided that the code must achieve 4 primary functions: appropriate responses to infrared and magnet signals, accurate ultrasonic navigation, continuous sensor input monitoring, and mapping. Flowcharting the rough algorithm and writing pseudocode aided in the organization and development of ideas, which then helped with their implementation later on. As mentioned, this flowchart was created as a rough outline for the code. It shows one large overall loop, which starts with reading the values of all sensors. First, it checks the parameters of the 3 ultrasonic sensors, allowing the robot to respond to sudden changes in distance from a wall, and have it either turn or back up accordingly. Next, the magnitude of any magnet, field, or infrared signal is checked, where the robot will back up if their value surpasses a parameter calibrated specifically to the source. The map will then be marked with the hazard. If nothing is prompted, the robot will continue forward and its path is recorded. Finally, if the ultrasonics read no interferences on all sides, the robot will drop off the cargo and terminate the program. Mostly following the logic of the flowchart, a pseudocode was then created to mimic an actual framework for the code. The pseudocode notes function calls, and placeholder parameters were given based on previous data collected from the sensors. Not everything was replicated from the pseudocode to the actual code, and actually, more situations were accounted for than that seen here, such as paths that branch from the main forward path, or functions inside the called functions that allow for precise calculation for the actions of the robot. 3 main functions were developed, with multiple sub-functions within them, taking in the parameters of the changing sensor input. For turning, an angle-based turning system was utilized in tandem with the ultrasonic sensors. When one of the ultrasonic sensors perceives a larger value than the wall distance, a sub-function determines how long the motors must run for it to turn precisely 90 degrees, which the robot then follows. This implementation allows us to avoid solely relying on ultrasonic-dependent turning, where the ultrasonics may indicate to stop turning even though the robot has not actually turned to the correct position. Our method was proven better in comparison and allows for accurate and precise turning. Again, using this angle-based turning method, the robot is also able to minutely adjust its position at a set angle if it becomes too close to a wall. Following the detection of a wall in front and on all sides of the robot, or the detection of an infrared or magnet source, the robot will then back up until a turn is perceived by a side ultrasonic sensor, and will turn if the map indicates that the path is unnavigated. This backing up function considers the orientation of the robot as well, which is updated every time the robot turns. This way, the robot understands its placement with relation to the turn, and can either turn left or right accordingly. The mapping function also utilizes this orientation system as well as a coordinate system to correctly output the charting of the maze once the program terminates. Each square in the matrix considers distance based on time and velocity, which each box being 40 centimeters long to scale. And, when either an infrared or magnet source is encountered, the map will note them to their corresponding number in the matrix. The reasoning for this method being the optimal choice is that it continuously relies on input comparison, allowing the robot to adapt to its environment relative to its positioning inside of it. Here is an example recorded during one of our robot's test runs. A 15 by 15 matrix was initialized, which allowed the robot to demonstrate the infrared and magnet source recognition, being marked 2 and 3 respectively on the map here. Both starting point and ending point are indicated by 5 and 4 as well. It is evident that the robot was capable of recognizing and following turns. After running the program, a hazard identification list was outputted both to the console and to an external CSV file. The source, parameter of interest, parameter, and its coordinates of location in the matrix were noted in the file as shown here. Once the program terminates, the map of the course was outputted to its corresponding CSV file as well.
By the final prototype design, the robot had both positive and some negative attributes. It was able to successfully detect magnets and infrared emissions, drop off cargo autonomously, and map the region it passed through. It was also able to retrace its own steps within the maze by backing up, thereby avoiding potential inaccuracies with a 180-degree turn or the chance to run into walls during this turn. However, there were also some clear design flaws, the most obvious of which was the changing friction coefficient with the ground as the robot moved. During the demonstration, bits of paper would stick to the wheels of the robot, reducing the quantity of friction between the wheels and the floor and making it more difficult to turn as it progressed through the maze. The turns gradually decreased in angle, creating a higher margin of error and a greater need for regular adjustments. Furthermore, the weight of the cargo also appeared to make the prototype unbalanced, affecting its turns and movements. The robot also defaults to driving forward if the path ahead is clear. Because of this and the lack of decision-making process involved, it could be possible that the robot doesn't always take the most efficient path to the exit. Finally, the robot also failed to give a signal after dropping the cargo off at the exit to the maze. Based on the target values set at the beginning of prototype design, the final robot was partially successful. Though the robot nearly made it to the end of the maze before hitting a wall, it only truly explored about half of it, which was well below our goals for overall disaster zone exploration. It also hit the wall a total of 5 times throughout our trials in the demonstration, and had to be recalibrated more often than we were initially aiming to. However, we were able to evade hazards at the desired distance of 10 centimeters, hold the entirety of the cargo in our cargo container, and open this container in the desired number of steps, which was 2. The robot also only moved suddenly once, which was during a particularly sharp turn. Therefore, it was fairly effective according to the team's recorded quantitative data and the original target values. Given a second opportunity, the team would undoubtedly make some changes to its design for future implementation. Ideally, the code would be made more concise with fewer conditionals so that it was easier to troubleshoot and would run more efficiently. It is possible to work with in its current state, but these changes would make it easier to use and it would be easier to alter overall. A counterweight could also be added so that the weight of the cargo does not affect the turning and driving mechanisms of the robot. A mechanism for the indication that the cargo was dropped off could also be added, possibly including but not limited to driving in a circle, waving a flag, or something similar. Another change could be motorizing the back wheels rather than the front ones. This would move the pivot position of the robot further back, making it less likely to run into walls. This would then allow for more efficient and accurate turns. Overall, the project was partially effective in its overall goals, but it was not without its pitfalls. However, its ultimate success is within the realm of possibility, and the implementation of these changes could lead to a more efficient and effective design overall. Thank you.